To understand the runtime of our B-tree operations, we need to discuss a couple of B-tree invariants. So what I'd like you to do to help us discover these invariants, I would like you to first add the numbers 1, 2, 3, 4, 5, 6, 7 into a BST in that order. And that should be pretty easy because we've actually already done that in this lecture. And then the other thing I'd like you to do is add those numbers into a 2-3 tree. In other words, a B tree where L is equal to 2. And the rule, by the way, for L equals 2 is when a node is overstuffed, you pass the middle item up. So give that a shot, pause the video, see what happens. All right, so for the first one, you should have gotten this terribly spindly tree. And then for a 2-3 tree, you should have gotten this really nice looking, beautifully balanced tree. Now, if you got stuck, let's walk through a little web demo. This is not created by me, this is someone else's code. So what I'm gonna do here is I'm going to say insert 1, and now I have a tree that has the number 1. I insert 2, and now we have a node with 2 items. We insert 3, and now what'll happen is, since L is equal to 2, the node splits, and we end up with 3 nodes, where the middle one moved up. We insert 4, we insert 5, we insert 6, we insert 7. And at that point, that node splits, overstuffs the roots, and then the root splits. And we end up with the tree that I showed here. Great. Okay, next challenge. What I'd like you to do now is pick a different order, adding the numbers 1, 2, 3, 4, 5, 6, 7, so that the resulting tree has height 1. So the tree we just did had height 2. I want you to give me an order where it's height 1. So pause the video, and I'll give you my answer. All right, so there's many possible answers, but one answer that I came up with is if you add 2, 3, 4, 5, 6, then 1, then 7, you end up with a height 1 tree. Let's see it again in that visualization. So 2, 3, 4, 5, 6. All right, so here I ended up with this tree, and now I'm going to add 1, and it'll end up in this left leaf, and 7, and it'll end up in the right leaf. And so in that way, we end up with a tree that actually has an even better height than we had before, so height 1. How did I come up with that? Trial and error, honestly. I just tried some stuff until eventually stumbled on that. So what we've seen here is 2 different orders. This first order we showed is actually the worst case order. This is a height 2 tree. That is the worst possible situation for a 2-3 tree. And here we have the best case, height 1. Now it turns out that no matter what order you pick, you will always get a bushy B tree. That's absolutely guaranteed. It might vary in height a little bit, as we just saw. This is height 1, the other one was height 2, but overall it's guaranteed to be bushy. Why? Well, because of the way that B trees are constructed, because of the rules we use for insertion, there are 2 very nice invariants. One is that all leaves must be the same distance from the source. We actually kind of discussed this earlier, that whenever the root splits, everything gets pushed down all one level. So it stands to reason that all leaves need to be the same distance from the source. There's another invariant that's a little trickier to see, but it has to do with the way that nodes split, and that is that a non-leaf node that has k items has to have exactly k plus 1 children. So to make sure those invariants make sense, here's a tree which breaks both. So first, let's observe that these 2 leaves, 1 and 5, 6, 7, that they're a different distance from the source. This one is 2, this one is 1. So this has depth 2, and 5, 6, 7 has depth 1. That's not possible. Secondly, a non-leaf node, for example, this 2, 3 node, this one has 2 items, but only 1 child. It should in fact have 3 children. So it should, if this was a valid tree, have 3 children. And this one should have 4, I guess, in this case. And this would be for an L equals 3 tree. So we haven't proven these invariants rigorously, but I'd like you to try thinking them through. And once you've fully digested them, you will find that they're helpful in understanding our runtime. So the reason that I really care about these invariants, the bottom line, is that these invariants, they guarantee that our tree is bushy. There's no possible way we're going to end up with imbalance or some leaf further from others or holes in our tree. It's going to be nice and beautiful and bushy.